All right, there is an awful lot to remember about mirrors. By the way, everything that we end up saying about mirrors is going to essentially be true about lenses as well when we learn about refraction of light as opposed to reflection of light. So there is a boatload of information that we need to know. There's a minimum level of information that you need to know, which would be something like what you're looking at on the screen right now, which is that real images are always inverted and inverted images are always real. There's no exception to that. If it's a real image, it's inverted. If it's an inverted image, it's real. And that's not something that, well, if you happen to remember that, it's helpful. You need to know that. Virtual images are always erect, and erect images are always virtual. So it goes back and forth. If you have a virtual image, then the image is erect. That means it's oriented in the same direction as the object. These two things are things that you need to know. We'll formalize this next thing that I'm going to tell you right now today, but informally we learned this yesterday, that the magnification of a real image is negative. And the reason why we know that to be true is magnification compares the height of the image to the height of the object. And if the image is in the opposite direction as the object for a real image, because real images are inverted, that means that the magnification for a real image is negative. For a virtual image, the magnification is always positive. There are some other details and you can see by these diagrams that I've made for your practice problems here, that the focal length is half of the radius. So if you measure the distance from the mirror to the center of curvature, that's called the radius, and the focal point is halfway between the center of curvature and the mirror, which means it's half the radius. What you have to do here is draw the images by remembering three things. And I will do this one just briefly. We'll do one together. That a beam of light that is moving parallel off of a particular place on the object will reflect through the focus. A beam of light leaving that same part of the object, and I always use the top, going through the focus will reflect parallel. And a beam of light, that's enough, by the way, for you to know that the top of the image, meaning the image of the top of the object, will be at that intersection point. So this is going to be where the image will be located. I don't know how well I constructed these diagrams, but if I draw a beam of light off of the top of the object that goes through the center, it has to reflect back through the center. And if I've drawn this properly, it will also meet in this point where the beams of light intersect, through the center, back through the center. You know, it's lots of beams of light. A beam of light coming off of the top of the object will strike the mirror here, and it will reflect to that point. There's gazillions of beams of light leaving the top of the mirror, and they all meet at that point. They all converge on that point. What's special about the three cases that we talked about, which I'm going to show you right now? Those are the three cases we've talked about. Through the center, back through the center, through the focal point parallel, parallel through the focal point. They're special because we know how to draw them. By the way, I don't know how well this is going to turn out. I've never actually tried this. But let me change to a different color of light. And I'm going to talk about the light coming off of this part of the object. So parallel will go through the focus. That's a vibrant green. Through the focus will go parallel. Doesn't quite match up. These ideally should be converging right here. It's not quite matching up. I just wanted to try it and see if it would work. stick with any two of the three known paths of light. Does anybody have any questions you would like me to go over? No? All right, so what we're going to do is take a look today at how we can avoid the ray diagrams. We can use formulas. Okay? So rather than you trying to sketch out a diagram to determine what the magnification will be, we actually are going to have formulas we can use to find the characteristics of images. We'll be able to calculate, if we have the right information, how tall the image is, whether it's a real or a virtual image, what the magnification is going to be, where the image will be located in relation to the mirror. One thing I should have mentioned, I talked about it a bit yesterday, but you were aware that real images are always on the same side of the mirror as the object. You might want to think that statement through. If you have a real image, the image will be located on the same side of the mirror that the object is on. In other words, it will be on the reflective side of the mirror because you can project it onto a screen. Virtual images are behind the mirror, which is, I know it's goofy because all images to me appear behind the mirror, don't they? But we're talking about the actual presence of light and where it converges to or converges from. So to begin with here, basically because we're dealing with circular mirrors, it turns out that these formulas relate what's going on. So I want to talk about the formula on the left first. And it's a beast of a formula. It says magnification equals the height of the image over the height of the object. And that means exactly what it sounds like. HI is how tall the image is. HO is how tall the object is. But that's also equal to negative DI over DO, which means DI is, if we look here, it's the displacement of the image from the mirror. It's how far the image is from the mirror. So H is measuring something vertically. D is measuring something horizontally in our diagrams, where it's located horizontally. So magnification equals HI over HO, which is equal to negative DI over DO. I just want to pause for a second and point out to you that that formula, which is on your formula sheet, is really three formulas. If you ever need to, you can use magnification equals HI over HO. You could use HI over HO equals negative DI over DO, or you could use magnification M equals negative DI over DO. It's up to you what you're going to use. I mean, if you don't know HI and HO and you want to find the magnification, then I guess you're probably going to use this one because it doesn't have HI and HO in it. Then we have this formula on the right-hand side, and this is unlike any formula you've ever used in high school science at any level. It's got reciprocals everywhere, which is really weird to rearrange. But it says the reciprocal of the focal length. So what's the focal length? How far from the mirror to the focal point? It's the reciprocal of the focal length equals the reciprocal of the displacement of the image plus the reciprocal of the displacement of the object. And I don't know, if you were to look at your formula sheet, I think it's written this way. I will very often say 1 over F equals 1 over DI plus 1 over DO. That's just what comes out of my brain. But where you put the 1 over DI and 1 over DO in the formula are not important because you're adding the two things. So the order in which you add them is unimportant. Now comes the difficult part. We have all these rules for when something is positive and something is negative. I will tell you right now, and you can make a note of this, that when you talk about the object, the displacement of the object, or the height of the object, these things are always positive. You never ever use a negative number for a characteristic of the object, like the candle flame. I don't care if we take the candle and turn the candle upside down. We're going to use a height of the object as being a positive number. Always. Everything else the height of the image, the displacement of the image, and the focal length of the mirror can be either positive numbers or negative numbers. And here's the problem. You will be lied to in a question. So, for example, you will be told in a question that a real image is produced with a height of 4 centimeters. And that's a lie. If it's a real image, it's inverted and the height is -4. So you're not going to be told these things specifically. You will be told that you have a convex mirror with a focal length of 20 centimeters, and that's a lie, because I'm about to tell you that a convex mirror has a negative focal length. Okay. So here are the rules. In terms of images, and this will come together, I hope, in a bit, real images have positive displacements. Now, I had to think about that, and I'll tell you why I had to think about it in a second. Virtual images have negative displacements. And I am going to tell you that I am not figuring that out. I'm not figuring out these two things by looking in my brain at where the image is. That's not what I'm doing. Okay? I'll tell you what I'm doing in a minute. Erect images, which, by the way, we can highlight something here for you if you like. Erect images which have a positive height, we know are virtual images. Right? This is something that you have to remember from yesterday. Virtual images are always erect. Erect images are always virtual. So one thing you will notice is that for a virtual image, the displacement is negative, but the height is positive. Whereas for a real image, real images have a positive displacement and they have a negative height. Inverted images are always real. And I'll just show you something now. I'll jump ahead. For any image, this is in your notes, just let it percolate in your brain. For any image, one of HI or DI is positive and the other is negative. Okay? So if you know that an image has a positive height, you know the displacement of the image must be negative. Specifically, if HI is positive, DI is negative. If HI is negative, DI is positive. Now, what kind of image has a positive HI? A virtual image, because a positive HI means it's oriented in the same direction as the object. It's an erect image, which means it's virtual. So when I wanted to figure out for a virtual image, let's just say, whether DI was positive or negative, what went through my head is, a virtual image has a positive height, so DI must be negative. Catch my drift there? I mean, if you can just memorize all of this, that's fine, but I'm giving you some tips here. If HI is negative, that's an inverted image, which means it's real, and if HI is negative, then DI must be positive. The two image characteristics are opposite. So those are the rules for the displacements and heights of images. Okay? We have rules for the focal length of the mirror, and you need to remember something here. This mirror that you're looking at, which is a convex mirror, will always produce virtual images. Okay? The focal length of this mirror is by definition negative, because the focal length is actually behind the mirror. That's where the negative comes from. The focal length of this type of mirror that you're looking at, which is a concave mirror, the focal length is out in front of the mirror, so that's why we say it's positive. This mirror, this concave mirror that I'm holding up, has a positive focal length. It has a real focal length. Can this mirror produce real images? Yes. Can it produce virtual images? Yes. regardless of the type of image this produces, the focal length is positive. It's got nothing to do with the image. It's a property of the mirror. So putting this all together, when you talk about focal lengths, and I'm just showing you this in a number of different ways, this isn't all in your notes, this refers to the mirror, not the image. A concave mirror has a real focal length. It actually does converge light to a point. Whereas a convex mirror, which I call a diverging mirror, has a virtual focal length. There's a lot to remember. All of this positive and negative stuff, like real images have a positive displacement because their height is negative, and virtual images have a negative displacement because their height is positive. And these two statements about whether the focal length is positive or negative, this is not an optional thing to know. If you don't know these, you will not be able to get the right answers to physics problems. I'll give you a second. There's a couple of you that are just jotting it down. I'll give you a second to finish jotting it down. And then we are going to look at some examples. So you might want to have your formula sheet handy because those formulas are on your formula sheet. They are, I believe, in the section under waves and light. Is my memory right on that? Let's get our formula sheets out and just check. I'll open mine up as well. Yeah, waves, under waves. We used to call it waves and light. I guess it's just called waves now. And they are the two formula in the top right corner of that section. So there's your magnification formula. There is your focal length formula. All right, let's give this a crack. I've already explained this. Example 1 says we take a 3 centimeter tall object and we put it 10 centimeters in front of a concave mirror that has a focal length of 2 centimeters. What are the characteristics of the image? So what we really want to know is what's the height of the image, what's the displacement of the image, and what's the magnification of the image. All of that will collectively as well tell us whether it's virtual or real. So I'm just making a list here of the things that we know. The height of the object is 3 centimeters. The displacement of the object is 10 centimeters. Those are always positive things, HO and DO. In this particular question, the focal length is positive 2, but I indicated that it's positive because sometimes the focal length is not positive. I'm really driving home the point here that the focal length is positive in this question. What is it about this question? Not working. Okay. What is it about this question that tells us we're going to have a positive focal length? Sebi? It's a concave mirror. And I'm going to go one step further and say it's a converging mirror. And I might as well jump ahead in time here and explain to you why I want to use the word converging. A converging mirror has a positive focal length. A converging lens, which you haven't studied yet, has a positive focal length. Right? Converging optical devices have positive focal lengths. But if I told you that a converging mirror is concave, but a converging lens is convex, then you would have to memorize concave mirrors have positive focal lengths, but convex lenses have positive focal lengths. Let's not do that. Let's just say converging devices have positive focal lengths. All right, so what do we do with this? Well, one thing we can do is we can use the equation relating the focal length to di and do, because when you look in your itemized list there, you know the focal length and you know do. And I want you to follow along carefully with these steps. Because it's a reciprocal relationship, the mathematics is a little bit goofy. And incidentally, I know I'm asking you to think and listen and write at the same time, but incidentally, this is a science class, not a math class. We don't want fractions, we're going to want decimals. So when I rearrange this, what I need to do first of all is get 1 over di by itself. This is not math where we're going to multiply by a whole bunch of stuff to get rid of denominators. Forget that. We're just going to take 1 over 2 minus 1 over 10. And I don't mean 1/2 minus 1/10. I mean 1 divided by 2 minus 1 divided by 10. I mean decimals. And I would like you to calculate what that is. For some reason, I think you're going to get 0.4. Now, when we do that, we get 1 over di equals 0.4, and the units of that are not centimeters. They're centimeters to the -1, or they are over centimeters, because this is 1 over a dimension, a distance. So how do you go from 1 over di equals a number with these units to di equals a number with the right units? You take the reciprocal. So at this point in time, you're going to go 1 divided by that answer. Just to show this to everybody in case somebody's watching the video, what you would do here is you would simply take 1 divided by 2 minus 1 divided by 10. We don't want to convert this to a fraction. It's, as I said, it's a science class. That is what 1 over di is equal to. So if 1 over di is 0.4, then di is 1 divided by 0.4, and that's how we get 2.5 centimeters. Now, by the way, this type of mirror can produce real or virtual images. I know right now that this is a real image. Because if di is positive and di came out to be positive, then hi is negative, and it's inverted, so it's a real image. What's the next step? Well, we would like to find the height of the image. By the way, I've already told you that it's a real image, and you know that hi has to be opposite in terms of positive, negative to di. So whatever work we do here to find hi, we'd better get a negative hi. We have to. Otherwise, somebody's been lying to you, or we've made a mistake. Just make a note. I'm only going to show this to you quickly, and then it's going to go away. But just make a note that that negative di means -1 times di. Right? That's what it means. So if di were negative, negative di would make it positive. Okay? That -1 means you multiply it by -1. So I'm going to substitute numbers in. I don't like to rearrange this equation. I like to put numbers in first. Hi over 3 centimeters equals negative of di, and di is 2.5, so negative of 2.5 divided by do, which is 10. You really have to be careful to keep things organized here. You got h and d and o and I. We cross multiply here. It's not a big deal. You're going to take 3 times negative 2.5 and divide by 10, and by my count, that's going to give negative 0.75. So, yeah, that's good because di was positive, hi is negative. I know right now, without actually doing a calculation, that this image is a lot smaller than the object. It's magnified downwards, so to speak. And the reason I know that is if the height of the image is 0.75, negative 0.75, and the object was 3, it's like 25%, which we're going to find right now because we have to calculate the magnification. So you can calculate the magnification by taking hi over ho. That's pretty straightforward. You're going to take negative 0.75 over 3 Was my math right there a minute ago? 25%, like 0.25? But it's negative 0.25. You could use this formula too. Right? We could take negative di and divide that by do, in which case we would take negative 2.5 divided by 10. Feel free to run either or both of those through your calculator to convince yourself that you get that magnification. Are we okay with that example? All right. So what have we learned about this particular situation? The characteristics of the image are that the displacement of the image is 2.5 centimeters, so it will be found 2.5 centimeters away from the mirror. With a little bit of thought, you will say it's 2.5 centimeters in front of the mirror because it's a real image. And I won't go there. And the height of the image is negative 0.75 centimeters, so it's inverted and only 1/4 the size, which is what the magnification is telling you. All right, let's try number 2. And examples 1 and 2 are really pretty straightforward. There's nothing really tricky about them. 2.5 centimeter tall object is placed 9 centimeters in front of a convex mirror that has a focal length of 4 centimeters. There is one lie that you've been told in that sentence, and it's the focal length is 4 centimeters. But, you know, if I don't know where you'd buy curved mirrors or what you would buy them for. Maybe I would want to buy a curved mirror because my reflecting telescope got dropped and the mirror cracked. Okay? And for some reason, it has a convex mirror in it. I would contact the company that makes those mirrors and I would say, I need a convex mirror for my telescope. This whole story is kind of garbage because you wouldn't have a convex mirror. It would be concave. But let's imagine it would be convex. The technician or the person who owned and ran the company would immediately say, what focal length? And all I would have to say is, 30 centimeters. They wouldn't send me a concave mirror because I said I wanted a convex mirror with a focal length of 30. I wouldn't have to say it's negative 30. They know that. So our itemized list here is that. The height of the object and the displacement of the object are always positive numbers. And the focal length is negative 4 centimeters. I didn't really point this out to you, but you notice that we worked in centimeters throughout everything, eh? We didn't have to convert to meters. And that's because either of those equations, if you have centimeters in each term, that's fine. If you have meters in each term, that's fine. So what are the characteristics of the image? We're going to start off with our focal length equation again. We're going to put in the focal length and the displacement of the object. And you're going to solve this for me on your calculator right now for DI. I don't think, unless I give you a written response question, that you have to worry about units in between here and your answer. We are going to be doing a lab with lenses where we have to use proper units, and you will have a written response question dealing with, I think, mirrors where we have to worry about that. But for now, you're going to take 1 divided by negative 4 minus 1 divided by 9. You're going to hit equals. Then you will take the reciprocal of that answer. Very close to negative 3, negative 2 point something, 2.7. I don't know, we'll find out. So that's what you get before you reciprocate it, and then you get 2.8 centimeters. Oh, right, I remember this now. I'm just including the decimals down here for a reason that is not important to the physics. Now we want to use our magnification ratio formula, is what I call it. HI over HO, which is the magnification, equals negative DI over DO. We can throw in the numbers. HI is what we are after. It's the only characteristic of the image we don't know yet. By the way, we had better get a positive HI because DI was negative. Yeah, Willis. Try it again. I know this is right, not because I remember the number, but because I've used the same sequence of slides for a few years now. So just try it again from the beginning. Just go 1 divided by negative 4. Don't forget the negative. Minus 1 divided by 9. So you're good now? Okay. So now we have hi over 2.5 equals negative 2.76923. Should carry all your decimals, by the way. I think maybe some of you might just put positive 2.77 in there, because you know negative is positive. Divided by 9, which is DO, and you get 0.77. By the way, this is just curious, and I don't know. I've tried to figure out what exactly is going on here. You get the exact same decimals in your HI as you do in your DI. And I don't know why that is, and it's not just a fluke up to that decimal place. When you run the numbers in a program like Excel to like 500 decimal places, they're the same everywhere. I don't know why that is, but I'm pointing it out to you because I don't want you to think that they will always be the same. Because students sometimes have misconceptions. They look at it and they go, oh, that's interesting. It's always the same decimals. That's just a fluke. Now we're going to find the magnification. So we can take HI, which we just calculated, divided by HO, or you could take negative DI, which is negative 2.76923, divided by DO, which was 9. And you clearly have to get the same thing. You get the same thing because HI over HO is equal to negative DI over DO. That's how we actually got HI, was assuming they're equal, because they are. So in this particular question, we have learned that it is a virtual image. By the way, you could have told me it was a virtual image before we started, because it's a convex mirror. And you could have told me before we started that the magnification would have to be positive because it will be virtual. And you could have told me before we started the magnification must be a number smaller than 1, because virtual images, which are always produced by this type of mirror that you're looking at, a convex mirror, are always smaller, whereas the virtual image produced by this type of mirror is always bigger, right? A lot bigger. That's why makeup mirrors are this shape. You don't want to use a makeup mirror like this, because you'd be looking in it and it's like a little tiny, tiny head that you're looking at. All right, so we learned that it is a virtual image. It's erect. The magnification is 0.31, positive 0.31. DI is negative 0.28, and the height is 0.77. Let's try a couple more complicated questions. A student wants to place an object in front of a concave mirror, and we want the image to be 1/4 the size of the object. Okay. From yesterday, we learned, and you can go back and look at all of the ray diagrams, that when you have an object in front of a concave mirror, when it's really far away, you get a tiny image, and as you get closer, the image gets bigger and bigger and bigger. Then it gets bigger than the object, and then it flips over and becomes virtual. We aren't told whether this image is virtual or not. Do concave mirrors ever produce virtual images? Yeah. So maybe it's virtual. And we need to know the answer to that. Let's assume, and maybe don't write this down. Don't write until I tell you to write this down. Let's assume it's virtual. Because in order for you to answer this question, and I haven't even gotten to the question yet, you need to know whether it's a virtual or a real image. Okay? Trust me on that. The question is, if you want to have an image that is 1/4 the size of the object, how far in front of the mirror should we put the object? What this question is saying is, what does DO have to be to get an image that's 1/4 the size of the object? Let's assume it's virtual, and let's see what happens. If it's virtual, the magnification is positive 0.25. And you're not writing this down, because I'll tell you right now it's not virtual. How many of you know it's not virtual? Just one or two, okay. Don't worry about it if you don't. Where am I getting 0.25 from? Well, if it's 1/4 the size of the object, then the height of the image over the height of the object is 1/4, which is 0.25. I'll come back to that. We also have 1 over f equals 1 over dO plus 1 over di. And we know the focal length. The focal length is 5. And I'm not going to put units in my work here because I don't want you to focus. Get it? I don't want you to focus on the units. I want you to concentrate on the math and the physics. Now the problem here is I cannot solve this for dO because I don't know di, right? But I know that negative di over dO is 0.25. So I'm going to solve a system of equations. I'm going to say I want to get rid of this di right here. So I'm going to take this equation and figure out what di is using that equation. Whatever I get, I'm going to dump it into the other equation below, and I'll have an equation that has do's in it. And everything I'm doing, even though I'm asking you not to write it down, is something you need to understand. So what do we get here? We get di equals negative 0.25 dO. We cross multiply and you get negative di. You get this when you cross multiply. So then it becomes positive di equals negative 0.25 dO. And this is what's going to go in here. So let's see what happens. We have 1 over 5 equals 1 over dO plus 1 over negative 0.25 dO. Forget for a second about how we're going to solve this, or how you would solve it. It can be solved because it's dO. There's no other variable. And you would solve this by multiplying both sides of the equation by 5 to get rid of this 5 in the denominator, by dO, which will at the same time get rid of the dO in each of these terms, and also by, I would actually use the negative here, you don't have to, negative 0.25, which would get rid of the negative 0.25 as well. So what happens? This is a Math 20 problem here. 1/5 times these three things, the 5 will cancel and I'll be left with the other two. I'll be left with negative 0.25 dO equals, when I multiply 1 over dO by these three things, the dO will cancel and I'll be left with the 5 times the negative 0.25, which I'm pretty sure, but sometimes my brain seriously skips a beat, I'm pretty sure that's negative 1.25. And then over here, when I multiply the third term by all of this, the dO cancels and the 0.5, the negative 0.25 cancels. I'm left with plus 5. Are you with me? Does that math look good? Solid? Things canceled where they should have? Well, you can solve this now. Add these numbers together and get 3.75. Negative 0.25 dO. Can you confirm for me that you get negative 15 here? Okay. It is at this point, I assumed it was a virtual image. It is at this point that I know my assumption was wrong. Because dO is never negative. What I've done is I've assumed something to be true, and it led me to an impossible conclusion. So that means whatever I assume to be true is wrong. It must be a real image. So now, after doing all of that, what you would do, and believe it or not, this is an exam question. This was on a diploma exam. What you would do is you would say, you know what? It is not. What's going on here? It is not virtual. It must be a real image. which means the magnification is not 0.25, it's negative 0.25. So we're actually writing this down. By the way, Evan, are you still pretty confident that you knew it was going to be a real image to begin with? Can you tell me what you were thinking?
Well, I was thinking, because it produces 1/4 of the image, it has to be real. It can't be virtual because when you're drawing our lines for our light paths, right?
Yeah.
If it was virtual, it was bigger.
It would be.
It would produce an image that's bigger than.
I don't, when I do that, and you're absolutely right, when I do that, I don't do the ray diagram in my head. I simply say, I know that this can produce virtual images, right? There's a virtual image right now, and I know this produces virtual images. And I know that the virtual images produced by a convex mirror are always tiny, so I remember that for a concave mirror, the opposite is true. So it's possible for you, by knowing that detail, by knowing that since this is a concave mirror and you're producing an image that's smaller, it has to be real, which you don't have to know to answer the question, but if you do, it makes your job a lot easier. Because you can bypass all of this stuff. So what we're going to do is we're going to set this equal to negative di over do. We're going to rearrange that for di. The negatives cancel. You're left with 0.25 do. We've got 1 over f equals 1 over do plus 1 over di. Focal length is 5. do is what we are trying to find. And 1 over di is 1 over 0.5 do. So we are taking this and putting it in for di. And we're going to solve this equation in the exact same way we solved the other one, except there's not going to be a negative there. By the way, if it were a math class, I would tell you, you probably shouldn't do that. You should probably write a set of brackets around the left side and write that stuff, and around the right side and write that stuff. When I multiply the 1 over 5 by that green set of factors, the 5 cancels and I'm left with 0.25 do. When I multiply 1 over do by that, everything cancels except for the numbers. When I multiply 1 over 0.25 do by the green factors, I'm left with 5. Again, please check my math in terms of canceling. I think that's all okay. I add 5 and 1.25 and I get 6.25 equals 0.25 do. So do is that divided by 0.25, which is 25 by my count. So the answer to the question is, with this particular mirror, you need to hold the object 25 centimeters away from the mirror to get that image. One more winding that's winding down a bit now. This one is not too difficult. I'm sorry. Does anybody have any questions with that final set of calculations here in question 3? So kind of winding down. This next one is, I don't think, as difficult as number 3, but it's still got a couple of twists in it. An object is 8 centimeters tall. Oh, okay. HO is 8. I don't know of what use that's going to be, but we can write it down. Produces a virtual image that's 5 centimeters tall. Is it? Is HI 5? Oh, I got a good poker face. Yeah, it is. It's a virtual image. It's a rect. HI is positive. I was trying to psych you out, and I think I reeled a couple of you in. HI is positive because it's a virtual image. Good? Okay. The image is 3.5 centimeters behind the mirror. Okay, well, you know, I could just say the image is 3.5 centimeters away from the mirror. I don't have to tell you where it is. So di is 3.5. Is it? It isn't. It's negative. Because if hi is positive, di is negative. And that's why it has no bearing on where it is. I mean, is it the case that virtual images are always behind the mirror? Yes. But if you know it's virtual, you know di is negative. That, I think, is really the only twist. What's the focal length of the mirror? Do you think, reading the question, you can tell me what type of mirror it is before we calculate the focal length? The object is 8 centimeters tall, and the virtual image that's produced is only 5 centimeters tall. Liam? It's convex, because the virtual image is smaller. I mean, and if it were a real image, by the way, then it would be concave no matter what. If you ever had a question that, let's imagine it said this. It doesn't, but let's say it said it produces a virtual image that's 15 centimeters tall. It must be a concave mirror. Convex mirrors, virtual images, which is all they know how to do, are always smaller. Concave virtual images, which they sometimes produce, those virtual images are always bigger. So what do we want to do here? We want to find the focal length of the mirror, which means we need 1 over f equals 1 over di plus 1 over do. Do we have enough information? Well, we got di, we need do. And you can find do by taking hi over ho equals negative di over do. So 5 over 8 equals negative 3.5 over do. So we need to cross multiply there to find do. .6, and it's positive. So we get do equals 5.6. Exactly 2, right? There weren't any other decimals. Okay. So we can roll with that. 1 over f equals 1 over do, 5.6, plus 1 over di, which is negative 3.5. Again, you just enter this as it appears in your calculator, no brackets or anything. We had better get a negative focal length, because we know it's a convex mirror because the virtual image is smaller. Can't do that one in my head, so I'll just 1 divided by 5.6 plus 1 divided by negative 3.5. It's going to be around 10. Just so you know, because I'm going to end up doing it without even realizing I'm doing it, you probably going 1 divided by the answer, right? What you will see me do, and sometimes I don't even think about it, is I raise it to the negative 1. Because when you raise something to the negative 1, it's going to go 1 over it. So I'm not doing this to be confusing to you. It's just something that I will do when my brain is on autopilot. So the focal length of the mirror is negative 9.3 centimeters. And because the focal length is negative, let's say the fact that it was a smaller virtual image, the significance of that was lost on you. You didn't really think about that. So you're at this stage, the fact that you get a negative focal length means it's a virtual focal length, which means it's a convex mirror. Any questions with that final example, number 4? So as you're working through the problems that are on page 17 of the unit handout for practice, you know, when you get a wrong answer, and maybe you won't get any wrong answers, but most people do. When you get a wrong answer, the first thing you want to do is ask yourself, did I miss a negative somewhere? Oh, it's a convex mirror, I should have used the negative focal length. Or it's a virtual image, I should have used negative DI. Those things have to be kind of at the forefront of your brain. Tomorrow we're going to move away from reflection and mirrors and start talking about refraction of light. You learned a little bit about refraction in Physics 20 of mechanical waves. We're going to learn in detail about refraction of light so that we can talk about lenses. Mirrors focus and produce images based on light reflecting. Lenses produce images and focus light based on refraction. So when light hits a mirror, it comes back from whence it came. When light hits a lens, it goes through the lens. There's a difference. So get to work on those. I want to take attendance and polish up my recording. It'll only take me a few minutes. We've got lots of time here to work on these. So I'll come around and help you out in a few minutes.